So this lecture is focused on Chapter 7, Part 1, Structure and Synthesis of Alkenes. Alkenes are hydrocarbons with carbon-carbon double bonds. They're also called olefins, meaning oil-forming gas. The functional group of alkenes is the carbon-carbon double bond, which gives this group its reactivity. So in terms of ethylene, it has sigma bonds from the sp2 carbons as well as the pi bond. So if we look at the orbital description, sigma bonds around the double bonded carbon are sp2 hybridized. Angles, as you already know, are about 120, and the molecular geometry is trigonal planar. Unhybridized p orbitals with one electron will overlap, forming the double bond or the pi bond. In terms of bond lengths and angles, the CC double bond is 1.33 angstroms. This is in comparison to a CC single bond, which is 1.54 angstroms. Also, there's a reduction in the CH single bond from 1.09 to 1.08. And again, the angles are approximately 120, 121 in this case, 116.6 in this case. The sp2 hybrid orbitals have more S character than the sp3. The pi overlap brings the carbon atoms closer. That's why we're getting a shortening of distance from 1.54 to 1.33. Pi bond in ethylene is formed by overlaps of unhybridized p orbitals of the sp2 hybrid carbon atoms. Each carbon atom has one unpaired electron in the p orbital. This overlap requires the two ends of the molecules to be coplanar. So in order for the double bond p orbitals to have this pi orbital overlap, it actually forces the molecule to be coplanar, as you can see over here. It can't undergo cis and trans isomers. There is no rotation around that carbon-carbon bond without breaking that pi bond, which is quite a hefty penalty of 264 kilojoules per mole. And in terms of elements of unsaturation or degrees of unsaturation, each double bond is equal to a single element or degree of unsaturation. Just to familiarize yourself or remind yourself, unsaturation is a structural element that decreases the number of hydrogens in the molecule by 2. It's also called index of hydrogen deficiency. So we had talked about this earlier on in the beginning of this semester. To calculate the number of unsaturation, first you have to find the number of hydrogens of the carbon, which would have the compound if it were saturated, then subtract the actual number of hydrogens and divide by 2. This calculation cannot distinguish between unsaturations from multiple bonds versus those from rings. It only just tells you how many degrees of unsaturation you have. So as we have done before, and this should be reviewed, to calculate the degrees of unsaturation for a compound with a formula of C5H8, first calculate the number of hydrogens for saturated compounds with 5 carbons. So in this case, it's 2 times 5 plus 2, which would be 12. Then subtract this number from the actual number of hydrogen atoms in the formula and then divide by 2. So actual would be 8 divided by 2, so there's 2 degrees of unsaturation. And it could be in the form of double bonds, at least 2 double bonds, 2 rings, 1 double bond and 1 ring, etc. In terms of heteroatoms, Halogens replace hydrogen atoms in the hydrocarbons, so when calculating unsaturation, you calculate halides as hydrogen atoms. Oxygen does not change the carbon-hydrogen ratio, so ignore it. And then nitrogen is trivalent, so it acts half of a carbon. So adding the number of nitrogen atoms when calculating, so what you want to do is add the number of nitrogen atoms when calculating unsaturation. So here's an example. First calculate the number of hydrogens for a saturated compound. In this case would be 10. Then it's 10 minus 8 divided by 2. Again, you're counting the halide here as hydrogen. So it has 1 degree of saturation. If we have an example with a nitrogen, again, you're going to calculate this. You're going to calculate the number of hydrogens for a saturated compound with 6 carbons. So that's here. And then you're going to add the number of nitrogens, which is 1, which would be 15. Then you want to subtract it from the actual number of hydrogens. This is 7 divided by 2, and so this would be 4. IUPAC. So you've talked about IUPAC a number of times. In terms of alkenes, you want to find the longest continuous carbon chains that include the double bond. Instead of ane, you want to change that ending to ene. And then you want to number the change so that the double bond has the lowest possible number. In a ring, the double bond is assumed to be between carbon 1 and carbon 2. So here are some examples. This is a former, would be a butane, but because it has an alkene, it will be 1-butene, or the other way you can do it is but 1-ene. So this is a fimer, 1-pentene, or pent 1-ene. This is cyclohexene, 2-butene, right? Now it's in between carbons 2 and 3, or but-2-ene, and 2-pentene because it's in between 2 and 3, or pent-2-ene. In a ring, the double bond is assumed to be between carbons 1 and 2. So for example, shown here, we are labeling this one because it'll give you the lowest number of this in terms of the substituent, 1, 2. So this would be 1-methylcyclopentene. Here, you want to make sure the numbering doesn't start off at the substituent, but at the actual double bond. So it's 1, 2, 3. So this would be 3-methylcyclopentene. If you have multiple double bonds, what you want to do is you want to give the double bonds the lowest numbers possible, and then use di, tri, tetra before ending in ene to specify how many double bonds are present. So for example, this is 1, 2, 3, 4, so this is a butane, but it's a butene, but there's 2, so it's butadiene because it's a 2 double bond. And you want to locate where the double bonds are. It's in between 1 and 2 and 2, 3 and 4. So it would be 1, 3, butadiene, or buta, 1, 3, diene. This is a 7-mer, so this is a heptane or heptene. And there's 1, 2, 3 double bonds, so that would be a triene. So it would be 1, 3, 5, heptatriene, or hepta 1, 3, 5 triene. Here's a cyclooctene. There's 1, 2, 3, 4, so it would be a tetraene. So it would be cyclooctatetraene, and it would be 1, 3, 5, 7 cyclooctatetraene, or cycloocta 1, 3, 5, 7 tetraene. In terms of cis-trans isomers, right? So now you're going to have to use that in looking at the name, or making the name. So for example, if we look at pentene, right? It's a 2-pentene, but this, because these are on the same size, this would be a cis 2-pentene, and look, the cis is italicized. So again, in an exam, if you're asked to do nomenclatures, you should make sure that the cis is underlined so that I know that this should be in italics. This would be the trans 2-pentene because they're on the opposite sides. And these are neither cis or trans because these are equivalent, so this could be both, and this is just on one side. So these are also called geometric isomers, similar groups of the same side, cis. Similar groups on the opposite sides are trans, and not all alkenes can show cis-trans isomers as we've shown here. In terms of cyclic compounds, these are some examples of cyclic compounds: cyclohexene, cyclooctene. This would be trans-cyclodecene, in which you see across the double bond it's on the opposite side. This would be a cis-cyclodecene, as you can see they're on the same side. So trans-cycloalkenes are not stable unless the ring has at least 8 carbons. And all cycloalkenes are assumed to be cis unless otherwise specified in their names. As shown here, this would be trans. EZ nomenclature. So using the Kahn-Ingold-Prelog rules to assign priorities to the groups attached to each carbon. If the high priority groups are on the same side, the name is going to be Z, voruzusamem. And if the high priority groups are on the opposite sides, the name is E for entgegen. So here's an examples. Here's a molecule of which is, you want to assign the priority to the substituents according to their atomic number. Propene here, and the propene is propene. Shown here, and we know that at the one position, because the bromo takes priority, bromo and alphabetically before chloro. And so again, priority goes by alphabet, so it would be on one bromo. The bromo takes priority because it has the highest atomic number versus a chloro. On the side of the double bond, so methyl, when you're assigning priority to the substituents, according to their atomic number, one is the highest priority. So these are on the opposite side. So substituents on this side, if they are on the same side, this one is the highest because this one has. So in this case, it's E, one bromo, highest, one chloropentene, and atomic number. And then on this side, same thing is italicized, so it's methyl versus hydrogen. Now, if the highest priorities are on the sure that groups are on the opposite sides as of the double bond, it's E. If the highest priorities are on the same side, it's going to be Z. So this one is actually on the opposite side. As a result, is E, and note it's italic. In terms of cyclic stereoisomers, you can have double bonds outside the ring that can show stereoisomerism. So if we look at this double bond, across this double bond in terms of priority between these two carbons, this one has higher priority because of the carbonyl. In terms of the methyl versus the ethyl has priority. As a result, these two are on the opposite sides. They're going to be the E. In this case, the high priorities are both on the same side, so this would be C. Again, in terms of stereochemistry and dienes, if there's more than one double bond in the molecule, the stereochemistry of all double bonds should be specified. So there's more than one. In this case, there are 2. We're going to be numbering it from left to right because this allows the substituent to be on the lower carbon chain. So then this would be 3 bromo octa 3,5-diene, and then to figure out whether it's E or Z. So if we look at this half of the double bond, you have bromo and the carbon being on the same side, so that would be 3Z, right? And then on this, you have this carbon and this carbon on the opposite side, so it would be 5E. So again, the Z and E's are italicized in parentheses, and it's 3Z, 5E, 3 bromo-octa 3,5-diene. Commercial uses of ethylene. It's been used, you can chlorinate to form ethylene dichloride, and then in the presence of base, generate vinyl chloride to generate the alkene again. You can take ethylene and react it with water and generate the alcohol, which is ethanol. You can add oxygen to it to generate an epoxide in the presence of silver, and then you can open up that epoxides to generate the diol ethylene glycol. You can polymerize to generate polyethylene, oxidize to generate acetaldehyde, oxidize again to the acetic acid. So these are different routes by which you can use ethylene as a starting material. Propylene, like ethylene, has a lot of reactions that can be performed on it. Again, you can do epoxide chemistry, in which you generate, in the presence of molecular oxygen and silver, generate the epoxide. This is called an epoxide. You can then take that propylene oxide, react it with water in the presence of acid to generate propylene glycol, the diol. React it with water in the presence of catalysts, isopropyl alcohol. You can oxidize that to generate acetone, right, the ketone from the isopropyl alcohol. And you can also polymerize to generate polypropylene. These are all examples of reactions, and many of these reactions you'll learn next chapters. In terms of addition of polymers, propylene, vinyl chloride, this is tetrafluoroethylene, can be polymerized to generate a polypropylene polymer in the case of propylene. Polyvinyl chloride, PVC, in the case of vinyl chloride, and tetrafluoroethylene. This is polytetrafluoroethylene, or PTFE, or Teflon, the coatings that you see on your nonstick pans. Heats of hydrogenation. So combustion of alkene and hydrogenation of an alkene can provide valuable data, especially to the stability of the double bond. The more substituted the double bond, the lower its heat of hydrogenation. That's key. So if we look at monosubstituted 1-butene or but1ene, in the presence of hydrogen and platinum, this will add hydrogens across the double bond, forming the alkene. The heat of hydrogenation is about negative 127 kilojoules per mole. If we look at a trans-butene, right, so 2-butene or trans-but2ene, this is disubstituted. In the presence of hydrogen and platinum, you form the butane. That heat of hydrogenation is lower. Goes from 127 now to 116, just because it is more substituted. So if we look at relative heats of hydrogenation, here's a terminal alkene versus the internal alkene that is trans. Right, that difference is about 11 kilojoules. Right, we had seen that it had the terminal alkene was 127 kilojoules, whereas in the case of the internal alkene that's trans, it's 116, so that difference is just 11 kilojoules, but they all go to the same products. So in general, the more substituted double bonds are usually more stable. If we look at the relative stabilities, you're starting off with ethylene that's unsubstituted, and then when you get monosubstituted, you are 11 kilojoules more stable. Now if we go to disubstituted, you can have cis, geminal, and trans, and of the three, the trans is most stable. followed by geminal, and then cis, being the least stable of the three disubstituted. If you go to trisubstituted, you are even more stable, and tetrasubstituted, the most stable. An important thing to note is that heats of hydrogenations are usually exothermic. So a larger amount of heat given off implies less stable alkene, because the less stable alkene starts from a higher potential energy. In terms of substituent effects, the isomer with the more substituted double bond has a larger angular separation between the bulky alkyl groups. So, for example, here, this is least substituted versus this isomer, which is more substituted, right? Because you have more substitution across the double bond. So, if we look at the separation of this, there's this methyl group here, these two methyl groups off this carbon, it's just going to have 109.5 separation because this is sp3. In this case, it's going to be sp2, right, because of the double bond, and it's going to have more separation. In terms of disubstituted isomers, the stability is going to be cis is lower, and then geminal is going to be even better, and then trans is going to be the lowest. So the less stable isomer has higher exothermic heats of hydrogenation. So of these three, the cis is going to be the least stable, and then the trans 2-butene is going to be the most stable. So I'm going to stop here because this is the midway point, and we're going to continue at the in the next part.